University of Kentucky. It's called Factors Affecting Inspection Staffing Needs for Highway Construction Projects. My name is Makram, and this paper was done under the supervision of Dr. Hala Nassereddine, Dr. Timothy Taylor, and Mr. Steve Waddle from the Kentucky Transportation Cabinet. Throughout this presentation, I'm going to talk a little bit about the background of this research, the methodology that we have adopted. I'm going to present some of the results which are limited to the scope of this paper, and finally conclusions on our further studies. So to begin with, the US public sector has spent nearly $92.5 billion on highway construction projects in 2018, and this is forecasted to grow to $107.74 billion in 2024. This might also increase even more now that the government is passing an infrastructure bill. But however, state departments of transportations or state DOTs do suffer from a problem, which is high staffing turnover. And this is happening on all three levels of staffing when it comes to the administration, engineering, and inspection. Administration staff is the staff that handles administrative tasks such as planning, scheduling, change orders, and budget management. Engineering staff that deals with design, estimation, traffic control, and conflict resolution. And also inspection staff, which oversees the ongoing operations to ensure that the work is performed as required in the contract. Now, one of the solutions that DOTs were doing in order to solve this high staffing turnover is that they were developing or creating forecasting tools. Those forecasting tools can allow DOTs to estimate the staffing levels needed for a project. They can facilitate the management of this project, and they can protect the firms from the damage that can be caused by initiating a project while they don't have, or while limited resources or limited labor resources are not available. So those are a few examples presented by Indiana DOT, South Carolina DOT, and Texas DOT about some of the forecasting tools. However, the gap that we're trying to address in our research project is that those tools, none of them was directly addressed to inspection staffing, or how can we allocate our inspection staffing resources when we want to undergo, plan, or initiate an infrastructure or highway construction project. And this is why, in order to address this gap, we created this study that's formed of three major tasks or three major milestones. First, we're going to be gathering data on completed construction projects from DOTs. Data included the project type, project size, project complexity, and with the cost and schedule performance of that project, in addition to the inspection full-time equivalents. We also, the next task is going to be to perform bivariate analysis to understand how did those characteristics affect the inspection FTE. And we're going to perform multivariate analysis to see if there's underlying relationships between those factors. And finally, we're going to be using our data and our findings in order to develop forecasting models to predict the inspection staffing for construction projects. Now, this paper is limited to tasks 1 and tasks 2A because this is still an undergoing research project, and this is what I'm going to be presenting throughout this paper. So to begin with, 241 project managers have participated in this study. They have provided data on 266 projects from 15 different states across the United States. The project types varied as follows. 48% of their projects were roads. They included all projects that are related to constructing new roads and expanding, resurfacing, or performing rehabilitation works on existing ones. 22% were for bridges, including constructing new bridges and replacing or performing rehabilitation on already existing ones. There's roadside safety projects, which included guardrails, lights, signals, stripes, signs, and landscape. And there was enhancements projects, which included ramps, curbs, shoulders, sidewalks, drainage, and retaining walls. When it comes to project sizes, this was the contract cost. It wasn't the final cost. It was the contract cost or the allocated budget for the project. 26% had a budget less than $500,000, 18% between 500 and 1 million. The most of the projects, or 34%, the highest percentage was for projects between $1 and $5 million, 11% for 5 to 10 million, 11% with a contract cost above $10 million. The project complexity, we adopted the definitions in order to define project complexity by a previous study done by Lee et al. We explained in the paper how we were able to, match every project to the type of complexity. 64% were minor complex projects, 24% were moderate, and 12% were major. We also collected data on the cost and schedule performance. They were collected as percentage overruns. For example, for cost performance, negative percentages indicated that the project was under budget, a value of 0 indicated on budget, and a positive percentage indicated over budget. And then the data showed that 45% of the projects finished within contract amount, 44% above contract amount, and 11% had no information. We had no information about it. Same thing for schedule performance. 46% of the projects were within schedule and 27% were behind schedule. So our response variable, or what we are trying to identify with our project, is the FTE of inspection. And we broke down inspectors to 3 levels: junior inspectors, intermediate inspectors, and senior inspectors. Also, we adopted the definitions from literature. So they mostly vary by the years of experience. Juniors have less than 2 years of experience, intermediate between 2 and 4, and senior at least 4 years of experience. And that definitely reflects on their duties. Now, this is our response variable. So what I'm trying to do in this paper is understand how do project characteristics affect this response variable, or the inspection FTE, throughout the projects that we were analyzing. So for the first question, the first bivariate analysis was to understand the impact of project types on the FTE of junior, intermediate, and senior inspectors. To do that, we drew box plots for every level of inspectors, and we tried to see how did the values change between one project type and the other. So I'm presenting the box plot for junior inspectors. I did not add all 3 to not overwhelm the slide or the paper, but those are the values for the intermediate and for the senior inspectors over here. So the difference in the FTE of each inspector level was statistically tested using the Kruskal-Wallis test to test whether at every level of inspection, if we had at least 2 project types that had significant differences when it comes to their FTE inspection allocation. And we found out that the Kruskal-Wallis yielded p-values for all 3 levels of inspectors. We also saw the follow-up Conover-Iman test to detect where those significant differences happened. We noticed that roads needed significantly more junior inspectors when compared to bridges, roadside safety, and roadside enhancements. Roads also needed significantly more intermediate inspectors when compared to roadside safety and roadside enhancements. Bridges needed significantly more intermediate inspectors when compared to safety, and bridges needed significantly more senior inspectors when compared to safety and enhancement projects. We also did the same thing for project size to see whether, when the increase of project sizes, if more FTE allocation was necessary for projects. We noticed that there is a positive trend, or there's a positive relationship between the FTE of junior, intermediate, and senior inspectors as the size of project increased. So in order to test whether this trend is significant or not, we used the Kinder correlation Tau-B test, and we found out that yes, it is significant. So the FTE of junior, intermediate, and senior inspectors did in fact significantly increase as the project size increased, or the size of the project increased. We did the same thing for project complexity. We tested whether the FTE increased or decreased as projects became more complex. We saw that it did increase for intermediate and senior inspectors, but not for junior inspectors. We tested again with the Kendall-Taubi correlation to see whether we yield significant p-values, and we did. We saw that as projects become more complex, we need more intermediate and senior projects. Intermediate and senior inspectors were allocated for the projects. Finally, when it comes to cost performance and schedule performance, respondents were asked, as I mentioned before, to note whether projects were ahead of schedule, behind schedule, over budget, or under budget. And we found that the Wilcoxon test, or the t-test, the non-parametric t-test that we performed between both categories, we found that projects that exceeded their budget needed significantly more junior and intermediate inspectors, but the senior inspectors were mostly the same. As far as the schedule performance, we noticed that projects that exceeded their planned time also needed more intermediate and senior inspectors, but they did not need more junior inspectors. So to wrap up, the paper analyzed historical data of 266 completed highway construction projects. We wanted to provide DOTs with a general idea on the impact of project characteristics on inspection staffing. We have to say that this paper is limited by the findings of the research project are limited by the the data that the project managers provided. And the paper is also limited to tasks 1 and tasks 2A, as it is still an undergoing study. So further studies, we're going to be performing multivariate analysis to see that if between those variables that we analyzed, whether we had underlying relationships that we did not see in the bivariate analysis. And then we're going to be using all our findings to develop those forecasting models that can help with planning, scheduling, and monitoring future construction projects. So thank you for listening, and if you have any questions.